All right, we are wrapping up our introduction to motion in one dimension. We've learned about motion diagrams, motion graphs, and motion equations, which can all be used to describe how an object is moving in one dimension. They have different uses and they give us different information, but each one of them describes very well how an object's moving, depending on how you want to look at them. Today, I'm just going to review those things and review some of the lessons that we were intended to learn along the way. I suggest when watching this video, you are welcome to put it on 2 times speed or something like that, and kind of just fly through it, watch it, and if you already know everything that I'm saying, then just kind of do your thing. And then if you hear me say something or you see something written on the screen that you don't understand, slow it down and rewatch it. This video is meant to be a review. I'm hoping everything I say I have said, taught, or given you guys an experience with already. So starting this off, we're going to do motion in one dimension. And let's talk about what we did with motion diagrams. Uh, I was going to say like the very first week of school, but this class is moving so fast that we're just not that far past the very first week of school. This object that I'm drawing here, this motion diagram, it's a pretty characteristic one, a pretty common one, that we have an object that is speeding up. And this they don't call them motion diagrams on the AP exam. Usually they'll talk about a snapshot was taken every second, or they'll say the positions were recorded at regular intervals or something like that. They avoid the actual term motion diagrams, but they're doing the exact same thing. And they're just not standard about what they called it, so I came up with my own name. So going through here, if we recall, each one of these dots represent a specific moment in time. For example, that first dot could be t equals 0, then our next dot is t equals 1, then t equals 2, then t equals 3, and finally t equals 4. So that would be like 0, 1, 2, 3, 4 going into our table. And as we went in there, we also learned that the dots then, where they're placed, represent the position at those different moments. So if we called this one, defining our reference frame as that being 0, that would be x equals 0. We'll call this x equals 2. Call this next one x equals 3. I'm sorry, x equals 5. This next one, x equals 9. And this last one, x equals 14. Uh, yeah, that looks right. So putting that also into the table just real quick while I'm remembering that I wrote all those numbers down. Uh, that gives us the position, and this is usually just the black dots and some kind of scale is what's given to you on the AP exam. And then they'll ask you questions like, well, what's happening with the velocity here? What is the velocity at this time? Or how does the velocity here compare to the velocity somewhere else? Um, so that's where these blue arrows come in, and that's where one of our big initial physics learnings came in, that we have this new quantity, this new idea called velocity, which is a vector quantity. It has both magnitude and direction. We know that the direction is always in this problem to the right, and the magnitude is always whatever the length of the vector is representing its speed. So this we can find the velocity magnitude by doing the change in position over the change in time. And working that out, we can figure out that the velocity for this area here was 2, and then 3, and then 4, and then 5. And that shows up on the table as well. If we are doing the difference in position between these two moments, we would get, I'm going to record it here. We're going to get a difference of 2. And then the difference between these ones is 3. And the difference between these ones becomes 4. And the difference between these ones becomes 5. This actually, each one of these average speeds actually exists right in the middle of the two, so I should have maybe set up the table differently. But we can't put an initial velocity in because we don't have information for what was happening before. We can make an assumption that it was 0, but we don't really actually know that. In fact, based on the way the acceleration is going, it was probably at a position of -1 before this. So anyways, um, Okay, so that's how we figured out velocity. And an important fact for velocity is that velocity gets more accurate the closer we get in time to a particular moment. So if I wanted to figure out the velocity for the whole period, this would be the velocity from time 0 all the way to time 4. Then when I'm trying to figure that out, I'm going to find out the average velocity, that's what that line means. It has a total displacement of 14 minus its initial position, 0. So that's our change in position, all over a change in time of 4 minus 0. Well, that's 14 over 4 for a value of 3.5 for our velocity. But looking at the table, nowhere, or looking at the motion diagram, nowhere does it actually go 3.5 meters per second, at least not shown. It probably did right around here somewhere. But that's not the speed everywhere, that's just its average speed. If I wanted to instead get an even better approximation for its speed at a particular moment, I could do something like, let's find out how fast it was going between seconds 2 and 3. And between seconds 2 and 3, it was at position 9 at 3, minus 5 at 2. And that gets us, and then 3 minus 2 for our times, which gives us 4 over 1 for a velocity of 4. And we're going to say, okay, well, that feels good. That's what the table says. But that's not perfectly accurate either, because it doesn't go directly from 4 to 5. There are time intervals between these points, between the seconds that our motion graph is sampling, where it's going, say, 4.1 and 4.2 and 4.3. And our motion diagram is limited because it can't give us that information. But that information does exist. And in order to get a truly exact velocity graph or instantaneous velocity, what we need a change in position over a period of time that is so small, so close together, that it's nearly instantaneous. But we can't actually do that in this class because this requires calculus. And so those of you guys who are taking calculus or planning on taking calculus, you'll do instantaneous velocities using calculus. But we're not going to do that in this class. The best we're going to do is we're going to try and get as close as we can to instantaneous velocities by choosing moments that are close together or as close together as possible. Or we choose moments where we can tell that the velocity isn't changing during that period. So once we figure out velocity, we also can notice that, hey, look at that. The velocity itself is also changing. And so that gave us our next quantity, which was acceleration. And with acceleration, we now have something that is a change in our velocity vector over a change in time. So we went from 2 to 3 here. So our change in, okay, we can't figure out either of these. Oops, those shouldn't be zeros. That makes it seem like we can figure them out. We can't figure either of those because we're missing values. But here we can find that we had an acceleration of 1. We had an acceleration of 1. We had an acceleration of 1. So during this period, with these known or these approximate average velocities, we can figure out that we had an acceleration of 1. And actually, in this case, because the acceleration was always 1, we know that the acceleration was constant during this period. So that's how we figure out acceleration, by looking at the changes in velocity. And there were some tips and tricks that I've shared a couple times now with velocity and acceleration. If we have a velocity vector going that way, we know it's moving to the right, and we have an acceleration going the same direction, we can conclude safely that it is going to speed up. If we have them going in opposite directions, then we know it is going to slow down. Oops, let's do that in black so it's all pretty. It will slow down. And that holds true even if the velocity vectors are going in the opposite direction. If they're both going to the left, then it's speeding up. The only difference is it's speeding up to the left. And then if we do the other version of velocity and acceleration vectors, If it's moving to the left, but its acceleration is to the right, it's slowing down. So that piece is meant to remind us that negative acceleration is not slowing down. It's the interplay between our acceleration and our velocity that determines whether something's speeding up or slowing down. So this recaps most of what we learned about motion diagrams and some of the important physics ideas that came out of there. So I'm going to pause this, stop this video so you guys can do whatever you want. And the next video we'll talk about motion.